Hello guys, today we will um, design an Intze tank, which is just a overhead water tank. Um, actually, nowadays or in the past, community like the city corporation or the um, district city, they used to construct a lot of them. Still now they are being used in Bangladesh and also in part of India too. So we'll see how we can design an Intze tank using STAAD.Pro. And on my YouTube channel, I have shown uh, how to design an Intze tank using hand calculation, actually, like just by following the manual method. And for that, I just use the book written by Sushil Kumar, and the title of the book is Treasure of RCC Design. Uh, this is an Indian book, and that's written based on Indian code, and that's an old book though, but still it's a good reference book. I use that one for my lecture, and we'll just um, design the instant that is on this book. We'll just use the dimensions, material properties, etc. And we will try to compare the results from hand calculation and also from the STAAD.Pro. So to begin with, um, uh, what is an instant? Um, as you can see in this figure, this is an instant. So uh, there is a difference between instant. You can see the word spelling INTZE and circular tank. So in the circular tank, uh, there is no conical dome like this one, and there is no bottom spherical dome like this one. So there will be just one single horizontal flat slab here. So there will be no conical dome like this one, as you can see, and no bottom spherical dome. So just over the staging, that means over the column, this vertical cylindrical walls will be there, and then the top ring beam and the top dome, there will be ring beam here too. So we'll try to see how can we design a circular tank. So you need to distinguish Intze tank from circular tank, and especially when the water capacity is too high, like several maybe uh, several thousand cubic meter. For example, the one we are designing, it's probably around 4 to 5,000 cubic meter. So that's going to serve maybe 50,000 or 1 lakh people. So when the capacity of the tank is too much, so that the circular tank becomes uneconomical, that means the bottom slab will be too thick, and that becomes uneconomical, then we go for Intze tank. So we can say that for larger capacity, Intze tank is an economical option to circular tank. Okay, so we'll just see how can we design Intze tank today, and the components are here. On my YouTube lectures, I just shown how we can design it by through manual calculation. I use that book as a reference, and that's in Bengali language though, but that's still a good reference. And I can share the book chapter of this book, which talks about circular tank and Intze tank. If you need it, you can just send me an email. My email ID is kobir.ce. If I write it here, my email ID is kobir.ce@gmail.com. So you can send me an email requesting the file, and I'll share it with you. So let's go to Intze tank design. But before we go there, I just need to talk about different parts of the Intze tank. As you can see, this is top dome, that part is top dome, and we call this part as the top ring beam. Then we call this vertical wall. This one is vertical wall. Then we have bottom ring beam. We call it B2. Let me annotate it here also. We call it B1. Then we call this bottom ring beam B2. Top ring beam B1. Okay, this is top dome, top one. This is bottom spherical dome. These are two spherical dome, and this is conical dome. You see, it's like a cone. Then we have bottom ring girder বলি, or we can say it bottom ring girder or just B3, simply B3, bottom circular beam or bottom circular girder, we will call it B3. Okay, and then we have columns, we call it staging. Sometimes in this book they also the author also referred it as staging, which consists of columns and also bracings. As you can see here, we have bracings too. We'll see it in few minutes. Let me show you one real example that I have just created in my class this afternoon. So you can see here we have these circular columns. I hope you can see the columns are circular, and then we have the square bracing. This bracing is connecting the columns. So we have 3 levels of bracing. Then we have this bottom circular beam. Then we have the conical dome. Then we have spherical bottom spherical dome, ring beam B2, ring beam B1, etc. Let me show you an rendering of this tank. So this is how the tank is going to look like. Okay, so that's top dome, that's ring beam B1, that's cylindrical or vertical wall. This one is just the ring beam B2. Then this is conical dome. The inside part is the bottom spherical dome. Then we have this bottom circular beam or girder. We have bracing, we have column, and then we have the foundation. I am not modeling the foundation here, but we can use we can model the foundation as either pin or fixed support or semi-rigid support. It depends on the soil condition. So we'll see it in later lectures. Today we'll just show how you can model the instant in STAAD.Pro, and we will just do another videos or maybe 2 on how to assign loads and then analyze and design different components of the instant in ETABS. Okay, so let me close this window because I want to start it from the scratch. And for that we need the dimensions too. So here is an economical proportion for inch tank. As you can see, we just calculate the volume of the tank. That means the requirement for storage, water storage. We just use the vertical or the cylindrical portion of the tank. Okay, we don't count this part, the volume of water in this part for storage capacity. For example, if I need to design a water tank for 4,000 cubic meter, we just use only this cylindrical portion to hold this water. So basically, if the height is S and diameter is D, then we know the volume of cylinder is pi r square S is equal to 4,000 cubic meter. If we assume S, then we can find the radius. So here this book has a good guide for economical design of inch tank. As you can see, if the diameter is D, then for an economical design we can assume the height as 2/3 of D. So basically, or if I don't use pi r square, then I need to use pi by 4D square into, we can use S as 2/3 of D. So you can find the D in meter here. Okay, so that's how we get the dimensions, and you can see all other dimensions depend on this D. So that's how we can get the proportions here. And considering that in my lecture on inch tank design, we used maybe I don't remember exactly, probably around 4,000 cubic meter. That means 4 lakh liter. So we'll just use that as the storage capacity, and for that we can use these dimensions. So the tank we are going to design, the dimensions are here. You can see the columns will be placed in a circular fashion. Let me show you. Sorry guys, before we start with the STAAD.Pro modeling, we need to have this information collected, otherwise we won't be able to show the dimensions. As you can see, the columns are placed in a circular fashion. Okay, so let me show you the foundation detailing, then you will understand better. So here is a circular raft foundation. and you can see the column locations here. So these are the columns. Okay, we have 8 columns, and the center to center dimension of the circle around which the columns are placed, that's 10 meter. Okay, this is 10 meter. So for modeling, we just use center to center dimensions, and as you can see here, other dimensions are given here also. We will take those dimensions from this picture. As you can see, the thickness of the top dome is 100 millimeter. Then the size of the ring beam B1, that's it's given here, 400 millimeter divided by the depth is 350 millimeter. So we'll get the dimensions from this tank, and for manual calculation, you can see my lectures on instant design. Let me just go now to the start profile to start with modeling. So I will come here. As you can see, the columns are spaced 10,000 millimeter, that means 10 meter apart, and we have 4 bays in the column, that means the staging, and the total height is 15 meter. So if we divide 15 meter by 4, then each part will be 3.75 meter. And then we have the bottom spherical dome height is 1.6 meter, the conical dome height is 1.68 meter, the vertical wall height is 6 meter, and the top dome height is 1.8 meter. Okay, so these are the geometry, and for section properties we will go to the detailed one. So let's just start from here. So to start with the STAAD.Pro, you just need to open your STAAD.Pro software here and just go to new project. We will use a space frame, and in this book the author used meter and kilonewton unit. So length unit will be meter and force unit will be kilonewton. If you want to use different unit, for example key feet, you can choose that too, but for this one we'll just use this unit. So go to next, and it says if the file already exists, we want to overwrite it. So if the file name is structure1, let me overwrite it and click okay, and this just click finish. So it has started the STAAD.Pro window. Okay, if you it has placed a grid on XY plane. If you don't want to see it, just uncheck this default grid linear view, it will be gone. So we will just start the modeling of Intze in STAAD.Pro by modeling the columns first. Okay, so to model the columns, as you can see, we have columns in a circular grid. Okay, so to model the columns, we'll just go to geometry and we will use run structure wizard option. So from that one, it has, you can see several options, like you can just model here and then import it in the STAAD.Pro window. That's how we are going to model the Intze. So you can see here we have truss model. As you can see, there are several truss models such as Pratt truss, Warren truss, Hoy bridge, lattice truss, Hoy roof, north light, etc. We have frame models where we can see we have bay frame, grid frame, floor grid, continuous beam, cylindrical frame, horizontal, reverse cylinder, which is vertical, circular beam. So we will use this reverse cylinder. Remember, it's frame model, it's not surface model. So this reverse cylinder, because our staging is vertical, we use this one. And for the ring beams, we will use circular beam. I will see it. And we have other options too. For example, we need to have surface models too, like conical dome, top spherical dome. You can see a spherical surface. We will use this for top and bottom spherical dome. And cylindrical surface, we will use it for vertical or cylindrical wall, and as also for conical dome, because those are surface, remember. So because we are going to model the staging, that means column and bracing first, we just need to go to frame model and reverse cylindrical frame. Okay, so you need to double click on this one. Now a pop-up window is here. It's asking for the length of the staging. So the unit, you can see it has changed. I don't know why it has changed, because we used kilonewton and meter for this window, right? But it's still asking me in feet. So you need to convert the meter unit in feet and then insert it here. So our height is sorry, I need to close it. Our height is 15 meter. So if I use my calculator, or I can open an Excel file to calculate it. Oops, Excel is here. Come on. Excel is here and I need to convert it. Let me just show you how can I do it. So let me put it in meter here, then we can convert it into feet. So 15 meter is equal to how much? So we need to multiply this with 3.281. We know 1 meter is equal to 3.281 feet. So into this cell. So that's 49.21 feet. Okay, 3.281 into 15 meter, that's 49.215. So go here and then click the reverse cylindrical cylinder, 49.215 meter, and it's asking for the radius. So our radius is 10 meter. You remember it? So how much will be 10 meter for this one? So I need to calculate it again and again. Let me do it in my hand calculator. Sorry guys, bear with me please. So that's radius is 5 meter. That means 5 into 3.281. So it will be 16.405. Okay, in feet. 5 meter radius. Remember, it's not diameter. So diameter is 10 meter. That means radius is 5 meter. So 5 times 3.281, that's 16.405. And we want it in a 360-degree angle. Sorry, I mistakenly pressed the enter button on my keyboard and it has made it. So what I wanted to do is just use how many columns? We need 8 columns, but it has made more than that actually. Maybe, I don't know, we can count it. So we don't want this, right? So what we can do is click this one again and it will pop up here. You can see it had number of base, we need 4, right? As I show you, we have 4 base along the length in the vertical direction. We have 3 bracings, so that means we have 3 bracings in between 4 base. And number of base along the periphery, definitely we have 8 columns, so it will be 8. And you must have 360-degree angle. So we just want to place in a circular grid. So you can see now it has changed, and when we press the left button of your mouse, just press it and move it, it will move also. You can see here if I have 8 columns or not. Just count it and you will see. One more important thing to notice here is you can see the beams that is connected here and there. They are just straight beams. Remember, they are not circular. I think I have shown you in our model. The structure was the bracing was actually straight beams, linear beams. They are not curved beams like the circular beams. Okay, so that's how you model your stage, and then you need to import it into the STAAD.Pro window. So just close it. It's now asking, would you like to transfer or merge this prototype into STAAD.Pro? Answer is yes. I want to bring it in my STAAD.Pro window. So we just want to place it based on the reference axis. Okay, so based on the origin 0, 0, 0, we just want to place it say at the 0, 0 level. So we don't want to change anything, and then click OK. So as you can see, your staging, that means columns and bracings, have been imported here. So I don't want to see the grids anymore. Let me just turn off or uncheck this option. So you have this staging here. Okay, that's the isometric view. Now, as we will see, we don't have these beams at the foundation level. So we'll just delete it. You can see this is the beam cursor. So when the beam cursor is active, just select it, see the isometric view to make sure that you have selected only those beams. Just delete it from the keyboard, and then this message will appear. It's asking whether you want to really delete these beams or not. Press yes. We will use the circular beam on the top two. So you can select like this, pressing the control key. You just go one by one and select all the top bracings too. We need to delete it because there is a circular beam at this point. So we need to delete these two. So just go one by one, then select it and then delete it. Otherwise, you can just go the positive Z view. You can see here it's view from positive Z. So since the beam cursor is on active only, it will select the beams and go to the isometric view. You can see the all 8 beams are selected. Press delete from keyboard and then press OK. So it has deleted also. Now you can define the sections and then assign the columns and bracings here. But what we will do is we will just finish the modeling all parts together, all parts, and then we'll define the sections, and then we will assign those sections to the respective elements. Okay. So now let me model the ring beam B3. As you can see, we have the ring beam B3 at this level, at the top of the column. So to model the ring beam, again we go to geometry, then run structure wizard. We go to frame model, because that's continuous beam is the frame also. So click on circular beam part here. So the radius is again how much? Do you remember it? In Excel file, it says the radius is, oops, oh, I calculated it on my calculator. So let's see how much it was. The radius is 16.405, and the angle must be 360, and it's asking for number of base along periphery. Along periphery তে আমি আসলে কয়টা বিম নিব। তো এখানে আসলে এটা যত বেশি আমি প্রোভাইড করব বিমটা তত বেশি সার্কুলার হবে। রিমেম্বার আমি যদি এখানে 18 ইন sorry, I went to Bengali. If I this is asking for the number of base along the periphery. So STAAD.Pro models the beam as a straight line between nodes, remember. So if I use, say, 20 nodes to draw a beam, it will divide the beam into 20 parts, and it will connect adjacent two nodes with a straight beam. So to model a circular beam, you need to input enough number of nodes or enough number of base so that it becomes a perfect circular beam. However, if you put too many of them, for example, if I put 100 of them, then it will be more perfect for a circular beam, but it will take more computational effort. So you need to have a balance between the computational effort and the accuracy of the model. So I'll just put, say, for example, 20 or 30 or 40. Let's apply 20 here. Okay. So if I say 20, then it has created a circular beam with 20 parts. You can see there are 20 nodes and 20 beams, and also you can see the the beam that is connecting two adjacent nodes, that's straight. So as you say, if I insert 100 nodes, that means 100, there will be 100 elements too, and that will be even a better circular beam. So accuracy will be even more, but that will take too much time for STAAD.Pro to calculate all the forces and then analyze it and design it, etc. So once we have it, then close this window. It will ask whether you want to transfer it and merge it in the STAAD.Pro main window. Answer is yes. And where we want to put it. So the height of the staging is 15 meter, right? And it's asking in meter here. So guys, please be careful with the units. You need to look look at the units on the window. So I will put it 15 here because my staging height is 15. So let's click OK. And it's asking whether I want to ignore the duplicate nodes. Answer is yes. And it's asking for a save option. Let me save it as Here, for example, say I will save it as structure 1, just for the sake. Oh, it already exists here. So let me place STAAD.Pro YouTube like this, and you can see the circular beam is here too, on the top. So if you go to Z view and then select the beam cursor, you can see the circular beam here. Okay, and you can see it's a better. It is not perfect, but it's a circular beam. Although the beams between the nodes are straight lines. Anyway, that's how we draw the circular beams. So our circular beams, what do we have in the instant? We have a spherical dome, and then we have conical dome. So let's draw the spherical dome first. Okay, so to do that, we will go to geometry again, then run the structure wizard, and we'll go to surface or plate models, because the bottom spherical dome is a plate or surface. It's not frame, remember. So plate type materials, you need to use plates. If it's a frame like the column beam, you need to frame. If it's a truss, then you need to use truss. So we'll click this one, and you can see we have several options, and for a spherical dome we will use the spherical dome, a spherical surface option. And definitely we want to use the top cap. A spherical dome is like if you cut a football, that means the soccer ball, and slice it into pieces, the top part, that one is our spherical dome, right? You can see it in the figure. So here we will keep this spherical cap, and then diameter of the sphere. So we need to have an understanding of this, and we need to go to the PDF file for this one. Diameter of the sphere and base diameter. What are these terms? Okay. So let me go to the PDF file and show you what are those. So let me annotate here. This is the spherical dome we want to model. So this is part a sphere, right? Like a football. And the radius of this sphere is that's the sphere of the radius. And what is the base radius? So you can see this is the base radius actually. That means that's the base radius. Base radius is 10 meter. How about the radius of the sphere? The sphere of which the bottom spherical dome is part of. So you need to have a calculation for this, and this book has the calculation. Let me show you. So it's here, the bottom spherical dome. Let me go there and show it to you. Design of columns, it should be above it. Design of ring in B2. Sorry guys, let me find it. Bottom spherical dome here. So you will see it. You can see the radius is 8.61 meter. That's the radius of the bottom spherical dome. You remember, the radius of the dome means the radius of the dome, the radius of the sphere. Okay, that's the radius. So the diameter will be 8.61 times 2. Okay, that's in meter. So let me go here again, and we need to have a spherical dome. So the diameter of sphere is 8.61 times 2, that means 17.22 meter times 3.281. So that's coming about 56.4988. And remember, you can see here the unit is in feet. It doesn't show here, but it's showing here. All units are in feet. So you need to insert it in feet. And base diameter is 10 meter. You remember it? So 10 meter times 3.281, that's coming as 32.81 feet. Okay. and top diameter is 0 because we don't want any hole here. And you can see the start angle it has calculated automatically, and end angle is 90. So if I want to show you what is meant by this angle, let me apply it here, then I will show you what does it mean about the start angle and the end angle. So we don't need to change these two, but we definitely need to change the number of divisions. You can see that's the latitude. So what is latitude and what is longitude? If I want to go to PDF, I need to cancel this. Let me cancel this and go there and show you what does it mean. So for this spherical dome, we have this is the view actually, right? That's the peak. So this is just a part of the sphere. That's the center of the sphere O. So this starts counting the angles from this horizontal plane. So this end is just this 90-degree angle. That's the end point, and that's the start point. So this angle is the start angle. Okay, start angle. And you see that's the base radius 10 meter, and this is the base radius 5 meter. That means base diameter 5 meter. And how about the latitude and altitude? So you just go like this. These are the altitude, right? So how many of them do you want in your model? So as I said, if you want 10, then there will be 10 slice. Okay, if you want 20, then there will be 20 horizontal slice. So there will be one top dome, and there will be 19 more slice like rings. And the latitudes are the vertical lines. These are the ones. Okay, how many of them do you want? So based on these numbers, your plate size will be either smaller or bigger. If you use too many of them, the plate size will be smaller. That means the calculations will be more accurate, but it will take more time for STAAD.Pro to give you the results. Okay, that will be computationally intensive. So I hope you understood what we mean by this parameters. Let me go back to STAAD.Pro again. So where is my structure wizard? Here. Again, what we want to do, that was, I forgot again. 8.61 times 2 times 3.281. So that's 56.4988. And then this is 32.81. And you can see when I inserted these two values, it has calculated the start angle automatically, and end angle is always 90 degree. And we want, for example, 10 divisions along latitude and maybe 20 along the longitude, or you can use maybe some more. So our start angle will be 0, and because we want a complete circle, so the end angle must be 360 also. If you want more, then you can insert 40, 50, whatever you want. As I explained, there will be more plates if you insert a big number here. But let's keep it as it is. You can see we have inserted 10 in the latitude. So you can count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. So we have 10 latitude, and then we have 20 longitude. Along the periphery, there are 20 vertical lines. So based on that, it has divided the whole surface into too many plates. Okay. Now we need to cancel it, and of course you want to merge it. And where will be the bottom spherical dome? It will be exactly at the top bottom ring B3 location. So that means top of the column. As I said, we will model whole structure with the centered line dimensions. Okay, so let me put it 15 here and then copy it. So as you can see, it has placed above the staging. That means I need to move this part down to there. So how can we do it? We can do it easily. Let me hide this part. So you can see my cursor here. Click this button, you can see, click this button, display node to node distance. So we will just move this top spherical dome from its current location to the top of the columns. So we need to see how much we need to move. That's why I just want to see the node to node dimension. So I'll just measure from here to here. So that's 12.212 meter. So I need to move this top spherical dome from this position by 12.12 meter downward in the negative y direction. Okay. So what we can do is, as you can see, we just need to go to the plate cursor. You can see my cursor here. We need to go to plate cursor to select the plate, because this is a plate element, right? This is a surface or plate element. This is not surface actually, this is plate element. So we need to go to plate element and have the plate cursor to select the plates. If you use just the beam cursor to select the plates, it will not select. If you use just node cursor to select the plates, it will not select. So you must select the plate cursor to select the plates. Okay, so select like this, then see the isometric view, and then right click your mouse on a blank space, and then you can see the move option here. So click move, and we need to move the dome by how much? My 12.212 meter, and I put that is a negative value, minus 12.12, because we need to move it down in the negative y direction. Okay, so let's click it. Okay, and it's asking whether I want to let me see, if any of the nodes of the entities being moved fall on existing members, do you want those members to be split at those nodes? Say you can say yes or no, whatever you want. And oops, it has moved too much. I don't know why it's doing like this. Let's go back. I don't think undo will work here. Let me just push you and fix it and come back to you again. Okay. Okay, guys. So we did something wrong. Let me explain you. Actually, as you can see in this figure, this took um, a oblique line between two nodes to measure the distance 12.212 meter. But actually, I need to measure the distance between two vertical nodes, right? So let me do it this way. So remove the dimensions just by clicking this part. You can see. Let's do it again here. So I just need to measure these nodes from maybe from let's me go this part, so that will be easier. So just click this one and then click this one, because they are on same vertical line. As you can see, the vertical distance between them is only 7.009 meters. So I need to move this plate just by 7.009 meter. Let's use the plate cursor to select it, and then right click on the cursor, move just by negative 7.009 meter. Okay, then click OK. Yes, and it's asking whether I want to merge those nodes, because at the same point we have nodes from the column, we have nodes from ping beam B3, and we have nodes from the plate. So there are duplicate nodes actually. If we want to merge them, we of course merge them, otherwise there will be orphan nodes. So let's delete the first one or second one, whatever you choose. Click OK, then yes. So it has removed all the nodes. Okay, and then you can click this whole structure options. It's showing there. So you can see the isometric view. I have the plates bottom spherical dome drawn here. Now what we can do, we can just draw the conical dome. If you want to see a 3D rendering, you can see it like this here. So that's the bottom spherical dome staging. things are there. So close it, and then we will click this one to remove the node to node dimensions. You can see you can use this one to show the node to node dimensions, then you can see use this one to remove the node to node dimensions. Okay, so now let's draw the conical dome. So to draw the conical dome, we need the dimension first. So how much is the height of the conical dome? The bottom diameter of the conical dome is 10 meter and the top diameter is 14 meter. And the height of the conical dome is 1.68 meter, right? So let's go to structure wizard again from the geometry option. Run structure wizard. Of course, we need to use surface plate models and then cylindrical surface. Although this is a cone, but we need to use the cylindrical surface, and we will have a different end and start radius. That's how we use cylindrical surface. Okay, and the length is, as we have seen, it's 1.68 meter, and we need to convert it into feet. So 1.68 into 3.281, that's 5.5120. Okay, and then start radius is 10 meter. You remember 10 meter. Sorry, start diameter is 10 meter. That means radius is 5. So 5 times 3.281, that's 16.405. And then end radius is 14 meter. 7 meter. 14 meter is diameter. So 7.3 times 281. So that's coming as 22.967. And of course, we want a whole circle. So it will be 360 the sweep angle, and we want it along the y-axis. So you just need to select end y-axis as 1, other should be 0. Okay, you will see the difference. You can see if you just change this and then draw it, you will see some one is along x-axis. If I put 1 and under x, it will be along the z-axis if I put 1 under z. So we want it in the vertical direction. That's why I put 1 at end of y-axis. Okay, and divisions along length. I mean, how many divisions I want? I will put maybe 10, for example. As I said, if you put a bigger number, then there will be more plates and it will take more time for analysis. Or I'll use maybe 10 for just to show you. But for real design, you can use a bigger number, so the plate size will be smaller and more accurate result will be obtained. Divisions along periphery, I will do it maybe 20, or you can use a bigger number. So that's how we model the bottom spheric conical dome. And you can see here, and we need to close this window. Of course, we want to merge it, and same again, it will be 15 meter. So duplicate nodes are there, as you can see. It's there too. Let's see a rendering of this part. As you can see, I have placed it correctly, right? Let's close this again, and then we want to draw the ring beam B2. We have ring beam B2 now here. So let's use the structure wizard again. Definitely surface plate models, and oh sorry, I need to use it as a frame model because we need circular beam. So the radius of the circular beam is in feet how much? So the radius is 7 meter. That means 7 times 3.281. It's 22.967. And angle is 360. We want probably 20 of them, or maybe 40, 50. You can put it there, and then we just import it. And what's the height now? So we had 15 meter for the staging. Then we had 1.68 meter for the conical dome. You remember this height? We have 15 meter from the zero, from the xz plane. Then we have conical dome height 1.68 meter. I hope you guys see my screen here. So 15 meter plus 1.68 meter. That's the height of the conical dome. That's why I am putting 16.68 here, so that it is copied exactly at this location. So You cannot see whether the beam has been copied here or not, but let's go this way. So go to the positive JIT view and then use the beam cursor. You can see this is the beam cursor actually. So that's beam cursor. Just select the top part. If there is a beam, it will be selected, otherwise not, because other elements are plate. So as you can see, we have drawn the ring beam B2 here. So after that, what we need to draw? We need to draw the vertical or cylindrical wall, right? And the height of the wall is 6 meter here and the diameter is 14 meter. So we go to the geometry, run structure wizard. We need a plate models, and that's cylindrical, and length is 6 meter. So 6 times 3.281 is 19.686 feet. Start radius and end radius, they are same. So 7 meter times 3.281, that's 22.967. Because this is a cylinder, so end and start radius will be same. For conical dome, we used a smaller diameter at bottom and larger diameter at top. And that will be same for this one, cylindrical wall, 22.96. And of course, we want 360-degree and we want along y-axis. So we may change it this way, and we want 10 of them along this line. Maybe we want around 30 or 50, whatever you want. I just want this way. Let's cancel it, and then of course, yes. Where do you want to place it? Above the conical dome. So that's again 16.68. You remember 15 meter plus 1.68 meter, that's 16.68 meter. So yes, and now let's see a 3D rendering of this. As you can see, it has been placed correctly, right? You can see the bottom spherical dome, then conical dome, then the vertical wall, but you don't see the beams yet. As you can see, these are the surface. We haven't assigned the thickness and the dimensions of the beams and columns yet. Once we assign those, we can see the full sections and 3D renderings too. So you see just some surface, you don't see the thickness of the plate here. Okay, so after the vertical wall, we have ring beam B1. To model that, let's run the structure wizard again. We need a frame model, circular beam, and the radius is 7 meter. That means 22.967, and angle is 360. We want 20 of them. You can use bigger number. Let's apply it. Close it. Of course, we want to import here. So how much is the total height now? So we had 15 plus then 1.68 plus 6 more. So we have, you can see here, 15 plus 1.68 plus 6. So it's coming to be 22.68. So let's see if it draws correctly. Of course, okay. And then you don't see the beam again. So what do? You just go to this one, use the beam cursor to select the beam here. You can see I can go up to this point, and because there is only one beam, that's how it selected the beams. And the cylindrical wall, it didn't select because those are not beams, those are plates. So you need to use plate cursor to select plate, you need to use beam cursor to select beam, you need to use node cursor to select the nodes, right? So that's how we model this one. Now we need to model the top dome, the last part of Intze. So the height is 1.8 meter here, but we don't need this. We just need the base radius, which is 14 meter, and we will need the radius of the sphere. So we need to go down to see how much is the radius of the sphere of which this dome is part of. So let me go there and show you how much is the radius. It's exactly here in the very top of the design of the tank. So you can see, let me annotate here. I will not annotate it. So the radius of the sphere, you can see the part of this is the spherical, top spherical dome. Okay, you can see the whole tank dimensions here too, and that's the radius of the sphere. So it's coming, r is equal to 14.51. So the radius is 14.51 meter. So you need to convert it into feet. It's asking for save. You need to save the models, otherwise it will not let you go further. So where is my structure wizard? Let me use the surface model again. Spherical surface, spherical cap. You can see start angle is 0 now and end angle is 90. So once we start modifying these values, you will see the start angle has been changed. So diameter of the sphere is 47.6073 feet. All units are in feet, remember. And then the base radius is 7 meter times 3.281. So that's 22.967. Okay, you can see the angle has changed automatically. So you don't need to change it. You don't need to calculate it. And divisions, maybe we want 20 of them. I don't know how many I put. I don't remember how many put we for bottom sphere and then conical dome and then a cylindrical one, but I'll just put 20 here. So apply, and then you can see we have a spherical dome again. Of course, we want to merge it, and the height is 22.68. You remember 22.68. So place okay. Oops. I think we put a wrong number there. The diameter looks very small. So what I will do is I'll just select them. You can see it's not selecting because I have beam cursor there. So I need to select this to select the beam. If I need to delete anything, I just press the delete, select those, and then press delete option from keyboard. It will delete it. So it has deleted the dome. Let me run the geometry again. Run structure wizard, surface plate models, spherical surface, and then I believe I have made a mistake in the calculation of radius. Maybe let's see. Radius is 14.51. I think I need to put diameter, but I inserted radius. So that's the mistake I made. Okay, I got it. So run the sorry, go here and then click it again. It's asking for diameter, but I inserted radius here. So let's check again. 14.51 times 2 times 3.281. So it's coming as 95.2146. And that's how much is that? Diameter will be base diameter is 14 meter times 3.281. So that's 45.934. Okay. And top diameter is 0. I want 20 of them, maybe divisions 10 to apply. So now let's copy it, insert it at 28.22.68. So this time the dimensions looks correct, but it has placed at the at a higher position, so we need to move it. Then we need to have the distance between them, so I'll just use this point to this point, the nodal dimensions. As you can see, let's see if it has measured the vertical line. I think yes. So we'll just use the plate cursor to select these plates and then move it. Click right button, move. By how much? Definitely we need to go downward, so we'll use minus on 12.710. So click OK, and it's asking to merge the nodes. Yes, of course I want to merge. Delete the second ones. Yes, it's doing all that. So hopefully it has placed in the correct position. You can see and let's see a rendering view too. We can just click this one to remove the dimension option, and then let's see a rendering view. So as you can see here, it has drawn all the components of the Intze tank. Only it's showing the shells as a surface and the line diagram of the beams and columns and braces, etc. So now as we have finished geometric modeling of Intze tank, we need to define the sections. That means the column dimension, bracing dimension, all circular beam dimensions, and then thickness of the plates, thickness of the domes, conical dome, spherical dome, vertical walls, etc. So to do that, we will just go to general. You can see here we have geometry option here. When we model it, it's in geometry option, and then we need to go to general, and then you will see this property whole structure button, and to define a section we will just go to define. To define the beams, columns, bracings, we will use define option, and to define the thickness of the plates we will use thickness option. So as you can see, our columns are circular. Let me go to this part again to see the dimensions. The dimensions means the section dimensions, okay, not the overall geometry of the tank. So I will come here. You can see this is the detailing. After design, we need to detail the tank too. So the detailings are here at the end of the chapter, after it has finished all the calculations for even for the foundations too. So the foundation detailing is here as well. You can see that's the foundation beam, and that's the raft, circular raft slab. So the column dimension is, you can see here they used circular column with a diameter of 650 millimeter. Okay, and then bracing size is 500 millimeter by 500 millimeter. That's the bracing. You can see the ZZ section. That's ZZ section. So the bracing is 500 by 500 millimeter, and that's the ring beam B3. The height is 1200 millimeter, and the width is 650 millimeter. You can see here too, the ring beam B3 height is 1200 millimeter and the width is 650. Whereas beam B2, ring beam B2, it has a width of total 1 meter, that means 1000 millimeter, but the depth is 600 millimeter. In our hand calculation, actually we have seen why we need bigger width than the depth for these beams. Okay, and the top ring beam is 200 plus 200 means 400 times such as 350, and the top dome thickness is 100 millimeter, then bottom dome thickness is 300 millimeter, the conical dome thickness is 550 millimeter. So these many sections we need to define. So let's go, guys. We need to define a circular section for our column, right? So I'll use circular, and then it's asking for the diameter. So how much is our diameter? It's 650 millimeter. That means 0.65 meter. You can see the unit here. Okay, so I need to click add. Then we'll go to rectangle. We have a top ring beam. I'll just define this way: top ring beam B1, then bottom ring beam B2, then bottom circular girder B3. This way, I'll go this way, and then we have bracing. So let's me define this. So how about beam B1? The dimension width is 400, depth is 350 millimeter. So the width is ZD. You can see ZD is the width. The bottom one is width. That's 400 millimeter, right? So I should put 0.40, and wide is the depth. That's 0.35. Let's go again. You can see here on the PDF. Width is 400, depth is 350. So we define this way. Then add. We have B3. B2 as 1 meter by 600 millimeter. 1 meter is the width. So ZD is 1 meter, and this is 600, right? 600, yes. Depth is 600. Depth is Y, remember. And of course, you can see the material is selected as concrete. We are using concrete. Even though it's reinforced concrete. So, but we must use concrete as the material here. For steel design in STAAD.Pro, we use the steel material, right? So we select steel there. It has option steel, stainless steel, aluminum, concrete. But because it's concrete structure, we use concrete here. So definitely we need to add. Then we have a beam, ring beam B3, which is 650 millimeter wide and 1.2 meter deep. So YD will be YD is 1.2 and ZD is 0.6, right? 0.6. And how much is the bracing? How much is the bracing size? 500 by 500 millimeters. So I will add another rectangle, which is 0.5 times 0.5. So you can see it's adding the numbers here. So you can see the reference number, and then section, and then material on this box. Now I need to define the thickness of the plates, right? So we just go to the thickness option there. It's asking for the thickness, and we want the plate thickness. So there are 4 nodes of the plate, and if you want to have a different thickness at the top and different, if you want to have different thickness along its span, for example, for the vertical cylindrical wall, which is 6 meter high, in the manual calculation, I think we got around 200 millimeter thickness at the top. You can see in the detailing here too. The thickness at the top is 200 millimeter, this dimension. And the thickness at the bottom is 350, you can see here. So if you want to use a different thickness, you can use it here too. So for the top dome, let me define it this way. I will define the top dome thickness, which is constant over the whole surface. That's 100 millimeter. So I will use 0.1. You can see it has changed all there because the thickness is constant everywhere. I'll just keep it and just add. Then we will add the maybe bottom spherical dome. That's 300 all over the area, all over the surface. So I'll just use 300 here again. That's the bottom spherical dome. Then I need to define the conical dome. So the conical dome thickness is 550 all along the span. Okay, so just 0.55. You can see all 4 have the same dimensions, and then I need to define the vertical cylindrical wall. So which has a top thickness of 200 millimeter and the bottom thickness of 350. So let me put it this way: 1, 2 is the bottom dimension, and 4, 3, 4 is the top dimension. So I will use 1 and 2 as that's the bottom dimension. That means 0.35. Okay, and this one will be 0.2 and the fourth one will be 0.22. Let me put it this way. So add. Now close it, and now I need to, as I have defined all the sections, I need to excuse me, let me check if it's recording or not. Yes, it's recording. Sorry guys. So as we have defined all the sections, we need to assign the sections to the geometry of this model, right? So we'll just go one by one. First, I need to assign the column sections. So you can see here on this box, I can just click on any section and it will be selected. So I want to assign the circular sections to the column. So you need to first select the circular section from this box and then come to this geometry window to select the beams where you want to assign this circular section. So we definitely want all the vertical columns, right? There are several ways to select it. For example, I can just go hold the control key and go clicking one by one, and it will select some of them. You can see it has selected the bottom 5s. We can go like this one, holding the control key button. I just select this way, or and then select this, and this. You can see you have selected only the vertical columns. Also, there are other ways to do it. So let's select this way. Select by beams parallel to y-axis. You can see the columns are parallel to y-axis. So it has selected all the columns. There are several ways to select it. You know it. So with that selected, we just need to click have this option checked, assign to selected beams, So this section will be assigned to the selected beams, and you just click assign. It's asking whether you really want to assign this or not. Of course, I want to assign it. You can see the section reference number is 1 here. You see the reference number is 1, and in the geometry window it's showing that reference number 1 has been assigned to this beams. Actually, that means the columns. So if you want to see a 3D rendering, for example, you can go to labels, then have the structure option, full section, apply, go. Okay, you can see we have a circular beam drawn here. As you can see, these are all circular beams. Do you see it? I hope you can understand it. So to bring the whole structure in the window, just click the whole structure, or otherwise you can go to view, then is it here structure diagram. It has the same option, full section, apply. Okay, we'll see it. If you don't want to see this 3D rendering, just simply go to geometry and then come to general. It will be gone away. Okay, so and then when you select it here, it shows the highlight. It shows the beams that has been assigned with this section. So with that one, we'll move forward. I need to assign ring beam B3. Yes, that's B1, then B2, then B3, then bracing. So I need to select this one first and then assign it to ring beam B1. So to select the ring beam B1, we'll just go to the positive Z view, and as you can see, we have ring beam cursor activated. If we just come here, it will select only the beam and then assign selected beams. Answer is yes, it has selected. There you see reference 2 has been assigned to ring beam B3. Then we select the reference number 3, that is the bottom ring beam B2. So we just come here and select this way. You can see the prismatic view, isometric view, it has selected only the ring beam B2. So we just click on assign to selected beams, and definitely I want to assign it there. Then we select the rectangular beam, that means circular beam B3, and we need to assign it to this beam, right? So I just make it a bit bigger. I'll use it this way, then come here and then assign it. So ring beam R4, reference number R4 has been assigned to. Then this is our bracing. So for bracing, you can go just one by one to select all of them, but that's not a good option, and you can select just like this way. Okay, so after selecting all 3 of them, you can see it in the isometric view whether you have selected the correct beams. If you not to deselect it, just holding the control key, select one of them, it will be deselected, and to select again, holding the control key, click here again. So with this one, and with the assign to selected beam checked in, just click on assign. It will assign the section to the bracing elements. Okay, and then we assign the surfaces. So let me see the full sections one more time. We go to structure, then full sections, apply. Okay, oops, something is wrong. I think I have made a big mistake. So this is a part of learning too. You can see the bracing sizes are really big. So as you can see from the dimensions here too. So let's learn from here. So what we can do, we definitely understand that we need to change the bracing size. So we go to edit option. As you can see, it has drawn as 5 meter by 5 meter. So I forgot to put the point before 5. That's how that's why it got this big number. So once you change this number, click on change, and as you can see, it has changed in the model too. So that's how it works. As you can see, we have all the beams assigned, right? We haven't assigned the plate thickness yet. That's why it's not showing here. So with this one, let's go to the plate thickness. The reference 6 is the thickness of the top dome. So we'll go to this one. As you can see, if it's beam cursor, it will not select the top dome. So you need to go to plate cursor, and definitely we don't want the 3D view. So I want to select it, then come here, and just by scrolling up with your mouse, you can just zoom in, and just by going down, you can move out. I'm just making it bigger so that I can select all parts, all plates of the top dome. So just select it this way, okay? It hasn't selected the bottom one too. So let me come down a bit more. As you can see, it has selected probably all plates of the top dome. I want to save it, yes. And then with this two selected, it's saying assign to selected plates. I want to assign it, yes. So do you want to see a rendering of this? You can see the rendering because this part is selected. The rendering showed only the selected part. But sorry, let's see the rendering or the full section now. So I will go to label again, structure option, full sections, apply. Yes. So it's showing only the frame elements. Okay. The thickness of the plates is not shown here. So to see the thickness of the plates, we need to go to renderings actually. So it's not showing that way too, but we can see it that the plate thickness 6 is assigned here. You can see array R6 assigned there. So we'll then go to which one? That's bottom spherical dome, right? So this part is a tricky part, and for that one, I'll go to this geometry, then click this one. I'll just select only the bottom spherical dome and the conical dome only. Let me select it this way. As you can see, I need to go to the plate cursor to select all the plates. It has not copied all the plates here. So now let's go to view. Either you can use view selected objects only, then in the main window it will show only the selected objects, or I can go to new view and then create a new window. The selected parts will be shown only in a new window. Your basic window will remain open and a new window will be opened only with the selected views. Okay, so now you can see the isometric view, or even you can see the renderings here, whatever you want. So what I will do is I'll just go to the plan view and then assign the conical dome first. So that's the tricky part though, as I said in the beginning. If we just define the sections and when we draw the geometry, we assign it, that's another way of doing it, and that may be easier. But the way I drew today is I just model all the parts and then define the sections, and then I am assigning those sections to the model. So this is a bit critical part for here. So with this part selected, if I don't remember how much is the thickness, let me go it's 0.5. That means it's the conical dome. So you can see from the 3D view, if I go to this window, the conical dome part is the outside part, right? Let me go to, oops, where is that window? It's behind it. So if we go to isometric view, that's the outside part is the conical dome, and the inside part is the bottom spherical dome. So if I see it from the top, you can see this part is the it's like a spider net, right? So the more space part is the bottom spherical dome, and closed spherical part is the conical dome. So with the conical dome thickness selected, I'll just go this way and select all the conical dome part. Okay, holding down the control key and then select all of them. If something is selected more than what you want, then you can just simply click on that one and it will be deselected. For example, I have selected this part of the bottom spherical dome. So holding the control key, just click on them and this will be deselected. So just go this way again, this part, delete, deselect this part. You can see this plate was not selected and this plate is not selected too. So come this way. This is extra. Let's go this way. This is select. Okay, so you can go to the isometric view and see I have selected the conical dome only, and with the conical dome thickness selected, I need to assign this section to the selected beams, and I will just assign it. So what I have left, let's close this window. Yes, I want to save it. Save, close it, and then you can see I have the structure assigned here. So if do you remember we haven't assigned the cylindrical part yet? This is the cylindrical section thickness, right? Let's see the thickness. The bottom thickness is 0.35 and the top thickness is 0.2. So I need to assign this to the cylindrical part. So just come to this part and then select all the plates here, just between these two, right? And see it in the isometric view. I have selected only the cylindrical wall and then assign it. So I have what left? The bottom spherical dome. I haven't assigned the thickness yet. So that's the critical part. You can just go to again this view, just have this bottom spherical part selected, and then have a for example view selected objects only. You can see only the selected part is shown, everything is gone. But if I want to bring all those back, just click on this display whole structure window, it will come back. I'll see. So with this one, I just can go to the top view and then select all the inside plates. That's going to be tricky because it's selecting only one part by one. So that's not a efficient way. What I will do is I have only the bottom spherical dome left, which has not been assigned with any thickness or section so far. So with that thickness selected, I will just go to select option, by go to missing attributes and then missing property. So it's showing only the part that has no attributes applied yet. So I'll go missing property, applied this section, and that's how it works. So I have assigned all those sections, right? You can see by clicking one by one, you can see where I have assigned this section. So just go one by one. This is the column, that's top ring beam 1, that's bottom ring beam B2, that's bottom ring beam B3, that's top circular beam, that's bottom circular beam, that's bottom circular what do we call girder or whatever, B3, and that's bracing, that's the top dome, that's the bottom dome, that's the conical dome, and that's the vertical cylindrical wall. So I have assigned all of them. Now I can go to label and then see the whole structure, how it looks like. You can see there, and then you can have a rendering too. It opens a new window when you want to see the renderings. As you can see, you can zoom in and just by scrolling up, and you can make this window bigger too. You can also whole window option as well, and you can see different parts of the conical Intze tank, right? So we haven't assigned the support yet. That's what we are going to assign at the very end. I hope you understand and you know now how to do it in STAAD.Pro, and I'll just finish it by assigning the support here. So let's go to the geometry again. We need to assign the support at the very bottom. So I'll go to plane, and then with the node cursor, oh no, I need to select, I need to define a support right first. So go to general again, then support. I need to create a support. So you can use fixed or pin. It depends on the foundation soil type or foundation type. For example, if you are using a pile cap, for example, and the soil is like the pile cap is not laterally moving or it's not settling that much, then you can use a fixed support for the water tank. or if your water tank is over a stiff rock, then you can use it as a fixed tool, because that's not allowing any rotation to the foundation. But at on loose soil, or if your tank is or the foundation is on loose soil, then you need to use the define it as a pin support, because that's going to allow the rotation of the foundation. So in most cases it will be pin support. That means it can resist the forces in all three directions, but it cannot resist the moment. So it depends on what type of foundation you are using. I'll just for modeling purpose use a pin support. Then selecting this pin support, we'll go to node cursor here and then select the nodes, all of them under 8 columns. Okay, you can see here we have selected only 8 nodes, the bottom of the columns, and then with this support to selected and assigned to selected nodes checked, we just assign it here. It will show the supports there true. So now you can again see the full section. So to see that, you can go to view again, structure diagram, structure full section, and then apply. Okay, so that's what it is. And then you can have a rendering too. Where is the rendering? Right, it's coming here now. So you can see the renderings. It's not showing the support though. So thanks guys for watching. I'll just conclude here today, and in the next tutorial we'll probably assign the loads and then make load combinations, and then we will analyze and design the tank, and probably we'll just compare our results from STAAD.Pro with the results from our hand calculation. So I hope you are enjoying it. So thanks for watching and have a good day.